Okay, so yesterday we saw with the aid of the non-equilibrium free energy, we analyzed what we can do with information, essentially, no? How information gets into the second law, and how can we design these optimal protocols for Maxwell demons. But we didn't care about the nature of the demon, or as you asked yesterday, if the demon dissipates, or if you need some work to measure, or you need some work to erase or something. We just said, we have this information, I don't care how I got it, and then how can I use this information? And that's it. And we had a lot of insight in this problem. Today, we are going to consider the nature of the demon. So we are going to analyze if all these processes, measurement, erasure, require some energy or some work, or if dissipation or thermodynamic cost. And for that, of course, we have to consider the demon as a physical system. So we are going to apply the same tools, non-equilibrium free energy and so on, but to the demon and the system as a global physical system. So we have to take into account the physical nature of the demon, and this is my seventh section, the cost of measurement and erasure. To do that, just recall a couple of things. That first is the free energy of a system. This is our basic concept, which is I will use this notation for the Hamiltonian. This is the mean value of the Hamiltonian. Sorry, I've used this notation as well yesterday. I explicitly include the Hamiltonian here, and this is energy over average over rho minus T Shannon entropy, and I will use the H for the Shannon entropy for X. X is the random variable distributed as rho X, and is the state of a system. Usually the microstate sometimes could be also the mesostate, but is a macrostate. And remember that we also proved this, that the work to go from one state to another is delta F. And also something that I will use now, because my system is going to be a bipartite system, so a system composed by the system itself and the observer or the measurement device. Then I will use this expression that also we derive the first day, I think, is actually the definition of mutual information. Remember, mutual information was hx hy minus hxy. Remember, it's the bits that I need to describe x and y without taking into account correlations, minus the bits that I need to take into account correlations. So is the bits that I save if I know the correlations of the two variables. And then from here, you can get that this is hx, hy, this is x minus mutual information. So the mutual information is like what tell us how different is the entropy of the compound system from the entropy of from the sum of each separate system. Okay, we introduced these relationships on Monday and yesterday, no? So, but I write them there because I'm going to use them extensively in here. So now we have an observer and a system. So I have my system, which is, well, this is the second part of the lecture, but it is my system would be one of those, an easy model, or the one particle gas in the Szilard engine, and so on. And I have my observer here. Which is interacting with the system in such a way that it gathers information, or it controls the system, and so on and so on. I will use letter M for the random variable defining the state of the observer, and X for the system. And let's look first at a measurement. How can we implement a measurement? Well, the simplest a scenario for a measurement, I will call it an ideal measurement. Well, first, initially, I will assume that they are independent. So M, X are uncorrelated. And I will assume as well that the Hamiltonian, the total Hamiltonian is the Hamiltonian of the observer. I mean, they don't interact. So they are separated, no? So the measurement is a kind of interaction, and the result from that interaction is that M and X will be correlated. So in an ideal measurement, you can take this as a definition. In an ideal measurement, my goal is that the system is not affected by the measurement. Let's say that in classical mechanics we can do that. No? So in the ideal measurement, so initially they are independent, and in the measurement X doesn't change. So the measurement doesn't affect the system, but M changes because it becomes, well, M adopts in an error-free measurement, will adopt the value of X, or a value compatible with X. So M is changing, and these become correlated. So now the probability to have, let's say, xm would be x and the conditional probability. And this is what characterized your measurement device. No, it's those who were yesterday in the exercise session. This is what characterized your measurement device. For instance, you can say, my measurement is left-right here, no? My measurement here is left-right. So M is left-right. X is any position. So this would be, in an error-free measurement, this would be if X is in the left part, M is left, and so on. You can also consider some errors that maybe you have some probability to say M equal left when the particle is right. So in this object contains all the information about the accuracy of your measurement. Okay, so this is, and we will assume that as well. So this is, the first assumption is that the system is not altered. It doesn't change. It only gets correlated with the measurement device. And the second assumption is that after the measurement, the Hamiltonian again is this one. So we have the same Hamiltonian. Of course, during the measurement, there should be an interaction, so the Hamiltonian cannot be the same all the time. But we will assume that before the measurement, the system and observer don't interact, and after the measurement, they don't interact. So we have an interaction that creates some correlations. You can have different definitions, but I think this is a acceptable scenario for the measurement. So for this type of process, we can apply this non-equilibrium thermodynamics, and it's rather easy because it is we have the free energies before measurement. What would be the free energy? I will use this notation for the free energy as well. Yesterday, I made explicit the dependency of the free energy on the Hamiltonian because I wanted to stress this dependency. But today I will call F the free energy of variable x, which is the free energy of the system in a state when the state is the random variable x. So in this case, the free energy before the measurement is the free energy of the system plus the free energy of the measurement device, of the observer, of the memory. We will call this as well a memory. Because somehow it stores as well the outcome of the measurement. Although memory is more when we study the cost of erasure, but this is a. So this is before measurement, and after measurement, what is the free energy? This is a sum because you can. They are uncorrelated, so everything is additive. No, the Hamiltonian is additive, and the Shannon entropy is additive, so everything is additive, and we have the addition of the two. So after the measurement, what do we have? So we have that now. If you want xm prime, let's call it like that. So this is the free energy of the whole thing. Sorry, I should have put it maybe fxm. With m, we know that this is before and this is after, no, because the change in m is from m to m prime. So now we have this thing, and this is the Hamiltonian of the system. In state x, the Hamiltonian of the observer in a state, let's put it this as a random variable, in the random variable m prime, minus t h. This is the energy of my whole system. And now I have to put the Shannon entropy of my whole system, which is t h x m prime. So this is the definition of the free energy for a system is the energy minus T times the entropy. Sorry, there is a KT here. K is the Boltzmann constant. And now I can use this split of the Shannon entropy, and then I get here the sum of the entropy of x plus the entropy of m prime, and with these terms I get the free energy of x and the free energy of m prime. But now I have the correlation. So the correlation is minus here, minus there. So I have a plus I plus kt I x m prime. So this is the free energy of the system after the measurement, and then the increment. The change in the measurement, let's call it like that, is this minus this. So the free energy of the system cancels, and I will call this the free energy of m prime minus the free energy of m. So this is how the free energy of my memory changes because of without taking into account correlations, plus KTI. And of course, this needs some work to be, remember that the work necessary to measure is bigger than this. So we get this expression that the work necessary to measure is given by the free energy is given by the mutual information. If we only think of the system, remember that what we did yesterday was just to think of the system. If we think of the system, what we see is that the free energy increases by KTI, which is what we got yesterday, but we didn't care about the, and the interpretation is different. We got yesterday KTI as a reduction of the uncertainty in my system because I know something. This is what we did yesterday. Today it appeared, I appears in another with another interpretation. Now it's the correlation between two physical systems, system and measurement. But you see that the correlation increases the free energy, and this will increase our capacity to extract work from the whole thing. But of course, because of this relation, it costs some work. So this is our first, this is the conclusion, no? That the measurement costs some work. This apparently is in contradiction with Bennett's approach, but we will see in a moment that it is not. Okay, this is for measurement. What about eraser? Let's say this is measurement, and now let's go for eraser. Well, eraser is much easier because the two systems are separated. To erase the memory, I only focus on my memory. And the memory goes from M to M prime. Sorry, to M prime to M. You know that eraser is not really erase the information. It's restoring the memory. This is more accurate. So it goes from M to M prime. And now it's very easy to calculate the increment of free energy in the eraser because it's Fm minus Fm prime. And this is this. So, and of course, this is a bound for the work that I need to do on the memory in this case if I want to erase. So I have to, all these operations, measurement and eraser, operations that we just didn't take into account yesterday, they have this cost. And the sum equals, well, the sum is bigger, and now you sum the two, and this cancels, and you get KT I, Xm prime. So this is the conclusion. This is what restores the second law. Yesterday we saw that you can extract KTI from some information. Here we showed that to create is to gather this information and restore your memory to the initial state. You need to put this work into the system. So it's the final story is very sad and disappointing because of course you cannot, the same word you extract is the same word that you have to invest to do the cycle. And here you have both Bennet solution and all this, we can, for instance, Bennet scenario would be this one.
You said you are considering demon and system together.
daemon and system together, yeah.
Is some external agent which is changing M to M dash?
Huh?
Some external agent changing M to M dash.
Okay, that's a good question. You can think, this is like we do in thermodynamics, that you don't care so much about the, of course, there is external agent doing this. Yeah, this is for sure, this is true. You need some external agent doing that. You can do it autonomously, and I will talk on that in the last section with this information flow. But here it's a kind of thermodynamic approach. You have a process and you don't care in thermodynamics as far as your process is reversible. You know the energetics, even though you don't, because everything is a function of a state. Here is a little bit the same. We are using functions of a state, if you like, which is the Fm. All these F's are function of a state. So we just care about the state before, the state after the measurement, and the state after the razor. And we get completely rigorous and results because this has been proved rigorously that you cannot work. But this is, you need external agent. You are right. Mm-hmm.
Is there any example of if M prime equal to Fm?
Yeah, you can do whatever you like here because f prime. Remember what is f? If you are thinking of this is of my memory, like for instance a normal memory, no, with 0 and 1. Remember that f is the energy, is the sum of Pm, Fm. Pm is the probability to be here or here. So now you don't, your m is discrete, and each state has a free energy which depends on how big is your well. No, you can have different wells or symmetric wells, minus kth m. So you can play with the two and make equal the two things. Yeah. Actually, this is Szilard, the Szilard-Bennet scenario. This is an example, no, of application. In this case, what do you have in this case? Well, the measurement is error-free. So when it is error-free, the I, remember, I is the entropy of the outcome. So you have this thing. And also in Landauer's and Bennet's and all this stuff, the memory is symmetric. So you have the same free energy here and here. This is the free energy of states of the system restricted to this well or this well. We will go into this in detail. So for a symmetric memory, this is always a constant. So F0 is equal to F1. And this is a constant. So we have only delta Fm. Delta F observer is just the entropies. Is Kt. The entropy, because of the minus sign, is m minus m prime. So if you plug in this there, you see that the measurement work has to be bigger than what we have here, Hm prime. Here minus Hm prime, so you get Kth Hm, which is the uncertainty of your x, actually, of your left right at the beginning. And this is not yet the Bennet scenario. This is Kt H m prime minus hm. Okay, this is for error-free and symmetric memory. You have these expressions. And now, if you start with the memory completely ordered, so you start with the memory has 0 entropy. This is the Bennet scenario. You could have this equals 0. No, you have a memory that is in 0. This is the Landau as well as scenario. And then this is equal to kth m prime, which is the famous kt log 2 in the Szilard. So here you see that, but you can have all the combinations. You can have error in the measurement, or you can start with a very disordered memory, and maybe even the measurement can order the memory, and then the eraser gives you more work than what you put in. So you can have all these things. Which the temperature, yeah, we are assuming, this is also a good question, that we are assuming that everything is in contact with a thermal bath. So you have two systems, you have an external agent, as we said before, and because for this scenario is when this is true. This is not true if you have two thermal baths or you have several things, or if this is also valid if the demon is not connected at any bath, because when you are not connected at any bath and you are in contact with something connected to a bath, it's like you are connected to the bath as well. So, but if you have several baths, for instance, the demon is in a lower temperature and so on, you can play a lot and probably you can get Carnot efficiencies and things like that, yeah, I'm pretty sure. But you need to extend this. The problem with this is that the nice thing with isothermal processes is that we have, for non-equilibrium isothermal processes, we have a thermodynamics. And I think maybe we can have a thermodynamics for other, but it's not well established, I would say. For isothermal processes, this is a rigorous, this is in a paper by Esposito and Vandenbroek that you can prove, they prove it for Hamiltonian dynamics, for master equation, for a lot of things, that delta F is really a bound for the work that you have to do to go from one state to another. What?
Before measurement, the measuring device is separate and the system does the path. So how will the measuring device interface with the path?
Yeah, you need how it will be in contact with the bath. No, we have to assume that, yeah, in the eraser you have to assume that the eraser is also done in contact with a thermal bath. Yeah, the eraser is done with the bath. Or it's a big system. I mean, it's the same as if it is a big system. If it is a small system and then you have inertia, and then probably it's if you have a microscopic memory, the eraser, it's not even clear what could be the eraser in that case. But maybe this is related with the second part of the lecture. Okay, so this restores the second law, but as sometimes happens in science, when you explain everything, it lost the magic or the.
Can I just check, like W measure, is that KTHM?
No, it's KTH. No, it's KTHM because you see you have to sum this plus this. No, this is the measurement. This plus this. Yeah. For me, it was when I was preparing the lecture, the notes, I also was surprised, but it's strange that the work to measure, it's just the entropy of the memory before the measurement. But it is not so surprising because the measurement is error-free. So somehow, well, this is what happens. Yeah, and I said, there is a kind of, all these results are kind of disappointing because we have, now we have a whole picture of the Maxwell demon, or at least the Szilard engine, no, with an agent and a memory and so on, which would be like something like that. You start with two systems, X and M, and correlate it. Then you correlate them. No, this is just a summary of what we have found. And then, and then you make the feed. This is the measurement. And then we would have the eraser, but in the middle we have the motor, no? All the operation. The motor is like, one can see that when one performs the whole thing, it's using these correlations, it's using these correlations, it's transforming the correlations into works. So at the end, it loses correlation. And this is the feedback step, let's say, which we don't care about. It must be smart, like it's all the protocols that we investigated yesterday. This is some kind of smart use of your energy, of your information to extract work. Usually we want a cycle, so we transform this into X again. So in a cycle, for instance, in the Szilard engine, we go back, X goes back to the same state. And here we have the eraser. And this is the whole picture. And if you think of the free energies, what is the free energy of each step? Well, we just calculated. No, this is Fx, Fm. This is what we calculated, Fx, Fm prime, Kti. Here we have again Fx prime, well, Fx plus Fm prime. And here we have again Fx, Fm. And the work to do each process is, the work here is bigger than what we wrote before, no? But delta F Kti. And here, if you calculate the increment, here you get is the work you get for in the feedback, so it's negative. And this is Kti. This is what we got in the first lecture, yesterday in the lecture, that you can extract for some feedback process you can convert this mutual information into work. And finally, you have the eraser, which is what we wrote is bigger than minus delta F observer, Fm. This is the whole picture of a feedback motor. No? You can, This one? This is a measurement. And if you look at this picture, you can say, this is nothing. And actually, I work in information thermodynamics with Jordan Horowitz for many years, and he saw this, and he said, yeah, now the Maxwell demon problem is solved. It's just a transformation from energy to correlation, and from correlations to energy. And it's just sometimes I convert. When I measure, I convert work into correlations. When I do the feedback, I transform these correlations into work again. And then, well, I have to erase, which is another step, no? And so with this idea in mind, with Massimiliano Esposito, they created a theory of flows of mutual information. So how correlations as mutual information can be convert it into work, and the other way around. So, and as I said, for them, this is the end of the story. For me, this is not the end of the story. I think there is more, because essentially what they have done, and this will be the lesson number 10, I mean section number 10, it's like a thermodynamic, it's like an extension of non-equilibrium thermodynamics. So you have, and they extend these pictures to autonomous systems and continuous time, because here we have steps, and they extend this to continuous time and everything, and it's a very nice theory of how energy goes to correlations and the other way around. And but for me, as I said, this is not the end of the story. There is another, for me, there is another ingredient in information which is physically important, which is what we have, I've mentioned several times that a memory device for me is something that requires stable states, informational states which are stable, like these ones here. No? What do you think of information? Information is something that remains in time. It's not something that is, it's not just a correlation, the creation of a correlation in an instant of time that fades away or that it's changing in time. It's something that it's robust, and for me, information is more related with the fact that you have several states, and that they are stable. They cannot jump from one state to the other, like here or there. And this also is a little bit, these two views, which I led for the last half an hour, and it's like, as I said, it's a controversy, you know, between people working in the topic. It's a little bit also like the controversy between analog and digital, or the dichotomy between analog and digital information. No? I remember I once asked Paul Davies, he's a physicist who has done some popular science on the origin of life and so on, if life could be built out of analog information, because, well, life is, or at least most of the information in biological species there are a lot of analog information, of course, in the brain and in the epigenetics and so on, but the core of the biological information, which is transmitted from generation to generation, is digital, is CTGA in DNA, no? So it's a almost philosophical question. What are the differences of analog and digital information, and what and if you can do the same things with the two? And let's say that analog is more the approach of Horowitz and Esposito. Is more like you have this mutual information, no? This I and X and Y can be dynamical systems, so you can, and they can correlate and decorrelate. So this is the approach of information flows. And what would be digital? Digital would be more like taking into account that for information devices you need this ergodicity breaking, because this is when you have this type of system, means that the system cannot jump from one region of phase space to the other. So you can consider this as a breaking of ergodicity. No? The easy model is a breaking of ergodicity. All the three that you have there are breaking the ergodicity at some point. So this is my approach, is that well, I don't think they are exclusive. I mean, you can have You don't have to say this is the good one and this is the bad one. But this is two interpretations of how to approach to the information problem. And this is what I will tell you now in the next minutes. This is 8 and 9. Okay. So now I will focus on the question of
ergodicity breaking is just a matter of time scale.
Huh?
When you say ergodicity breaking,
yeah, that's a good question that I forgot to tell. When I say ergodicity breaking, it's not a rigorous ergodicity breaking. It's for instance, here, when you have a particle in a two double well potential, and the barrier is, let's say, 50 kT, the system is ergodic. It's still ergodic. Because, I mean, the system with the bath, no? You have your Brownian particle with the bath. This is ergodic, mathematically, it's ergodic. But the time to go, for the particle to go from here to here, it's the exponential to 50, no? It's e to the power 50 or 10 to the power 40, something like that, which is effectively is ergodic, no? So it's not ergodic. So I talk about an effective ergodicity, not a mathematical ergodicity. So actually, I don't know if this has been, if this has a mathematical rigorous formulation, because ergodicity has, you have the ergodicity theorem, which tells you the average over time is equal to the average over phase space. And here we don't have I don't have something like that, but intuitively it's clear that you have a loss of your system cannot explore the whole phase space. And even in an easy model with a particle with finite number of particles, the phase transitions are really ergodicity breaking. You have ergodicity breaking only in the thermodynamic limit. Otherwise, there is a very small chance that all these spins flip in the other direction. And this is truly ergodic. No, if this is a piston, the particle cannot go there. But we are talking about effective ergodicity breaking. So in these three examples of Szilard engine, you can see that there is the measurement and all this stuff, but there is a step that we didn't discuss, and it's actually what creates the easy model, which is the phase transition that you did here, the symmetry breaking. When you insert the piston, the particle can get trapped in one of the two regions of the phase space, left or right, and here is the same. So you have a symmetry breaking, which is the process that really starts everything in the Szilard engine. So the idea is to and I would say that this is like creating information, because what is a symmetry breaking? A symmetry breaking is that you create, suppose you have your double well, no? You create a double well, and or in the easy model is even easier to see. You create some macroscopic uncertainty. When you cross the critical point in the easy model, the system gets positive magnetization or negative magnetization. You create some kind of macroscopic uncertainty, and we will see that this has as a consequence a reduction of the phase space. Okay, we will see now in a moment. So this is what I call creating information. This is why I call the symmetry breaking creating information. Yes, creating information in some parameter in the macroscopic form. Okay, to analyze the symmetry breaking, which is this process, I have to go back to the idea of informational states and the idea of local free energies. Not nonequilibrium free energies, but local free energies. And this slide is to just justify my approach, is that, okay, when you have this type of process, your equilibrium state is this one. But this is, and it has a free energy, which is this one here. the partition function minus kt log partition function. But is this really useful? Because this state, if the two parts of the phase space are disconnected, I can, for instance, now lower this well, and the state doesn't change because it is the same as before, because it cannot equilibrate, and longer an equilibrium state. Or if I look at a single system, be here or here. When I say single system with, well, with average over time, this doesn't matter. So this equilibrium free energy is not so useful in terms of describing your system. And actually, people in thermodynamics know that. For instance, people studying ice, or they don't look at the free energy of the whole configurations of ice from water to ice in a transition. They prefer to talk about conformational or local free energy. And the conformational energy is called conformational because you have different, when you have this coexistence of phases, you can have, each one is a different conformation. So you calculate the partition function only in the phase space, in the region of the phase space where this phase, where this system is present, and the free energy there. This is actually the free energy that when I wrote in the informational states, when I wrote the non-equilibrium free energy is PMFM minus HM. This is the same. This is the local free energy of my system. Okay, so this is the typical setup in a memory. So I have a memory here. For instance, it could be 2 bits. So I have different states, and when the memory is a memory is just a system where I have regions of ergodicity. So and the system cannot cross in a reasonable time from one region to the other. I have my partition functions and my conformational free energy, or free energy of a state. I will say free energy of a state. And let me remind you that the global equilibrium state is given by this formula. These probabilities, this is the probability of being in each region, and the equilibrium is this one. So usually I will have local equilibrium. What I have is local equilibrium, but these PMs are arbitrary. And only when these PMs are equal to this formula, the whole thing is in equilibrium. But this is going to happen very rarely. It's going to happen very rarely. Okay? Okay, so what happened in a symmetry breaking? A symmetry breaking is when you create the memory, actually. Your memory, or you start with a completely ergodic system, and you create barriers that partition the phase space into different regions. So let's look at this example where you have here, there are no barriers, so the system here can explore the whole phase space, but you cross a critical point, and now the system is confined in one of the regions. Let's say gamma 1. So this is something that you can get it for free. A symmetry breaking is a compression that you get for free. It's like when you put the piston in the Szilard engine, you get a compression for free, but you pay a price that you don't know in which size is the system. Here is the same. You get a compression of phase space for free, but you don't know in which region of the phase space the system is. You can be in gamma 1 with probability P1, gamma 2 with probability P2, P3, etc. Okay, this is the scenario. And the nice thing is that one can very easily prove the following thing: the free energy change of the system, understood in this case with conformational free energy difference. The free energy difference after the critical point minus the free energy before the critical point. So this is the change of free energy in the critical point is given by this formula, and this formula is just the probability to be in one of the phases. So we have this nice formula that in a critical point, so when you create information, This increases the free energy of your system, so capacity to do work, if you like, by a quantity kT log P1. Of course, this increase, this is conformational energy, so you don't know in which of the three instances the system is, so the price you pay is that you have an uncertainty of the phase. But for the free energy is this thing, and then this will require a measurement to really detect in which of the regions is. Okay, so we get an increase of free energy. This is positive because it's less than 1. You have an increase of free energy for free, if you like. For free? Well, for free, but with an increase of the macroscopic uncertainty, which is the uncertainty of in which region the system is. And we have this formula, and well, I think this is interesting by itself that in each of these phase transitions, or when ergodicity is broken, you have this reduction in this increase in the free energy, or even you can say that it is a reduction of the entropy, although finally this reduction of the entropy is compensated by the uncertainty of the macroscopic uncertainty. So it's not against the second law, but it's like a transfer of uncertainty in the microscopic to an uncertainty in the macroscopic world. Well, here you have the reverse process, which is from coexistence of phases. You cross a critical point and you go to, you again go to ergodic system, and you can have another expression like that. And it was nice that we could do an experiment with the people, with the group of Dmitry Petrov. Unfortunately, he passed away years ago. And the experiment we made the experiment with 2 optical traps and a single particle. So it's a double well potential, if you like. You have 2 traps, and we separate the traps. So the particle has to decide in which trap gets trapped. And this is the potential as a function of time. So you see here there is a minimum, and here is the double well potential, and this is a trajectory of the particle. So in this case, the particle chose the upper well. And because we want to, we measure the heat and the work and all this stuff here, but we wanted to bias one of the wells because our formula has the probability to be in left or right. So we want to change this probability, and we put a field. This is an electric field, uniform and static field, which bias one of the two wells. And this is the result. This is the entropy production measured by measuring the Shannon entropy and the heat and the work and things like that. And this is the Shannon entropy, which is negative. This is the production entropy. Remember that there is no, it's not the total production entropy because you have the uncertainty of which well you have. You have always a kT log 2 of uncertainty. And this is our prediction, or this is an inequality, but it should be equal for a quasi-static process, and these were the results that we obtained. Here we change P, which is the probability to be in the left well, by changing the potential, the electric field. And also for the symmetry restoration, you can do the same. Okay, so here you see, as I said, it's like this transfer from micro to macro uncertainty, micro entropy to macro entropy. But when one thinks of not ensemble of systems, but single systems, like the universe is a single system, no? It's true that it has undergone a lot of symmetry breakings. I mean, we are a symmetry breaking. The whole DNA of in the biosphere the DNA library, let's say, of the is a symmetry breaking, and it's a unique one. I mean, there is no. It's hard to say that this is an uncertainty because we could compare. You have to think of an ensemble of Earths where all the possible evolution histories have happened, so which is crazy. So this conformational entropy, which is the conformational entropy, remember that in each symmetry breaking decreases, paying the price that the macroscopic or the informational entropy increases. But somehow this increase of entropy, I don't know if it's physical. So, oops. So, sorry, I have to go through all these things. So this is almost kind of philosophical question, but it's a question of really to understand the evolution of the Earth or the universe in terms of entropies and things like that. Do we have to use really the total entropy or the conformational entropy? And if we have to use the conformational entropy, then it can decrease. It can decrease. So not, I mean, by tiny amounts if you want, KT log 2 for each bit, but it could. Okay? And in the last half an hour, no? So this is for creating information. So you see that this is a problem. This is just, I would say that this is an open, not an open question, but an open line of thinking, let's say, to continue. But it's the first approach to what are the energetic consequences of creating information. This is what we have done. Now, since I'm very obsessed with the role of symmetry, of ergodicity breaking into all this business of Maxwell demons and so on, with Rahul Marathe, who is now in Delhi, in 2010 we came with a nice example of how ergodicity breaking can affect what we have seen of the Szilard engine. So we were able to, with this symmetry breaking, not symmetry breaking, ergodicity breaking processes, we were able to create a Szilard engine that works without a measurement. But of course, it's not so. So it was not. It was a very modest Maxwell demon because it was with only one particle and no thermal bath. So there is no thermal bath, and it's only one particle. You can say, well, this is not thermodynamics and this is not the statistical physics. But I will try to convince you that we can learn things from one single particle, because actually it's a single particle, but it starts in the microcanonical ensemble. So you don't know. It starts with some energy, but you don't know exactly the microstate. So it's a kind of statistical mechanics still. Microcanonical ensemble for one particle. So the particle is in a box, like we have seen before, and obeys Newtonian dynamics, so it's dynamic, so it's just bouncing in, this is 1D, so it's bouncing and in the walls. And the collisions are elastic, so there is no anything. There is no bath. There is no friction. Anything. It's completely Newtonian without friction. So energy is conserved and so on. Okay. So now we do the following. We raise the barrier of a given height, which would be important in the following. The width is not so important, but we raise this barrier, and the particle. Now it doesn't get trapped necessarily. If the energy of the particle is bigger than this, it will still bounce between left and right. It will not get trapped. Here it will slow down because of the potential, no? And so, but the particle will go like that again. Now we move the right wall to the left, and now it's something interesting that. If the energy of the particle is not so big, it starts to bounce, and because this is moving, now it's the velocity is decreasing. No, if you collide with a wall that is moving, you slow down the particle slows down. So you lose energy whenever you hit this wall, but here, no, here is elastic. So you start to lose energy, and at some point your energy is below the barrier, and you get trapped. But because you always lose energy here and never here, you always get trapped here. So we don't need to measure because the particle is going to be in this. We know for sure that it's here. Now we compress the other part because it's empty, and we can go here and we make a cycle. And this cycle, because we have this expansion, and in the expansion, the energy the particle is lowering the energy, and this energy is something that we get as work, if you like. So we can cool down the particle. We can get energy from the particle.
Isn't there any cost in the second stage?
Huh?
While you are inserting that potential VB, isn't there any cost?
Yeah, there is a cost, but you can do it as small as you like with the width. But there is a cost. Yeah, I think there is a cost. Yeah, there is a cost, but you can do it as small as.
Is it some time-dependent fashion?
Yeah, you have to do it as. Yeah, you are right. There is a small cost, but it's bigger. This is essentially. This is not. You can do it as far as you like. So think of not extracting work. Think of cooling down the particle, which is, and then you see that when you increase this, yeah, you are putting some energy into the particle. That's true. But when you do this, you are extracting energy from the particle. And finally, the particle can even be completely at rest at some point. We will see this in a moment. So, of course, what I told you works only if the velocity is such that the initial energy must be bigger than VB, but but must be bigger, yeah, but not very big, because if I move my wall up to some point, maybe it never gets energy below the barrier. So the whole thing works for a specific value of the initial energy. If the initial energy is low, then when I raise the barrier, the particle gets trapped, and the whole idea fails. And if it is very large, it never gets trapped. So it's only working for a specific value of the velocity. Actually, this is what happens with the position. If you have a phase space, no, position and speed, this is what happens when you raise the barrier. The position. It's true what you said, that this increases a little bit the energy, but we can forget about that. And when you make the expansion, these particles here lose energy. Those doesn't lose any energy. Those also lose some energy, and those here remain in the same. And at the end you get that.
If you are doing it repeatedly, the next time you'll have to reduce VB.
Yeah. Then what's the idea? First, it works only if I know the energy at the beginning. This is why it is microcanonical. I need to know the velocity, because otherwise it doesn't work. But I don't need to know the position. So let's say I can extract energy from a microcanonical state. And what are your questions? If I repeat it, no? And okay, this is in one shot that this is the final energy, and this is as a function of the initial energy. So only in this window, which is the blue window, the energy decreases. And actually, if I'm below, the energy can increase a lot. And if you calculate the average of everything, if you don't know, or if, for instance, if the initial state is thermal, actually there is a theorem that tells you that if the initial energy distribution is a decreasing function, there is a theorem by Campisi that tells you that any cycle puts energy into the system. You cannot cool it down. This is a theorem. So here we need we need to know at least where it doesn't need to be completely microcanonical. It could be you could have some uncertainty, but But you need to know the initial energy of the system. So this is the idea. And as you said, you can repeat this. When you repeat this, of course, you cool down your particle in the first run. So you have to adapt your protocol. So it's not completely cyclic. You have, because your protocol works only for a specific value of the energy. When you decrease the energy and you go, you repeat the cycle, you have to modify the height of the barrier. But using this protocol, which is easy to calculate analytically, you can reduce the entropy, the energy of your system as much as you like. This depends on the speed of your protocol. But if the speed is very slow, you can go down to zero. I mean, you can go down to as close to zero as you like in several repetitions. Okay?
So, sorry, at which stage do you extract work again?
Here.
Yeah. And it's just extracting the thermal energy of the particle until.
Well, thermal is kinetic energy, because this is kinetic energy. Yeah. And this is one shot, one run, one cycle, 2 cycles, 3 cycles. So you are decreasing the energy. And at the end, the problem is that the uncertainty in the velocity, you have, when this goes to zero, the energy goes to zero, this interval where the machine works becomes smaller, and the uncertainty on the energy becomes bigger, and then you cannot do better. Huh?
Alpha, beta, gamma?
Alpha, beta, gamma here, sorry, but I think they are. Alpha is the speed. Yeah. Alpha is the speed of the walls. Units are L = 1, and time probably is in such a way that the mass is 1 and everything is 1.
If you move with very slow velocity, then you can approach.
Yeah. This is for how. The problem is that if you don't do, the problem is, and actually I will show you in a moment, but it's easy to understand that when you do this very slowly, the uncertainty in the energy is much. I mean, if you do it fast, the orbits start to spread, and then you get a lot of uncertainty in the energy. And this uncertainty in the energy prevents you to use the protocol in this when the energy is very low. When the energy is very low, you don't have precision in the energy enough to run the protocol.
In the last step, putting energy to the particle, right?
Where?
In the last step, beta.
This is the velocities. Yeah. Thank you for pointing me out, because I forgot that beta is the velocity of this wall and alpha is the velocity of this wall. And this is important because sometimes you can get when the particle has a smaller velocity, then you can be here. This is why when the particle has a small energy, then when you raise the barrier, if the energy is below the BB, the particle gets trapped either here or here. If it gets trapped here, it's the green curve, and you have to make a compression, so you put a lot of energy into the system. And if it gets trapped here, you get the red curve. So this green and red are for particles with less energy than the barrier, and particles follow this or this with probability 1/2. So you have to read, and this is the average. Actually, the final energy is the green and the red. The green is for particles here, and the red for particles here. You get it? Because when the energy is below VB, when you raise the barrier, the particle gets trapped, either left or right. So you have the two possibilities. Okay?
And beta is fixed, right?
Huh?
Beta is fixed by the initial energy.
Beta is, this is, the protocol is only, you have to design the protocol following this recipe.
No, but then I will not be able to go back to the original state in the phase space, right?
Yeah, you go back to the original, well, it's shifted, but well,
No, but only in the position space, but in the momentum.
You go, I mean, the whole system goes back to the initial potential, if you like. The system to go back really to the original, the system doesn't go back really to the original one.
Configurational spaces.
No, I will show you now that I think I have. The system does something like that. This is a layer of energy, and when you we already raised the barrier. No, this is velocity and this is position, and this is, you see the particle is slows down here, and when you raise the barrier, when you start moving like that, in each collision the particle loses energy, so it creates a kind of a spiral. It's a little bit complicated, and you get this kind of a spiral, and at some point it gets trapped. This is what happens. Okay. So,
can you think of this as network between the walls, which are 0 temperature, and the particle, which is at non-zero?
no, because zero temperature is very different from Newtonian dynamics. Zero temperature means that you have friction and no noise. So particles go to the ground state. And no bath means no friction, no noise. Okay. So, but from the point of view of phase space, and this is why we call this section Maxwell demons in phase space, this is interesting to first, because maybe we can generalize this. I will, Suri left, but the next slide is by him. But, he had to leave to take the plane, I think. It's first, we have to know what is going on. Besides being a nice idea of how to cool a particle and so on, there is something happening here because it looks like something that cannot be done. And actually, if you think of the second law, there are two properties of Hamiltonian dynamics which are closely related with second law. One is the Liouville theorem that tells you that if you start with a region in phase space and you evolve with a Hamiltonian, the volume must be the same. Maybe the shape is very strange, but it's the same. And the second one, who is less known, is that the volume enclosed by an energy shell is what is called an adiabatic invariant. Adiabatic invariant means that it's an invariant when the evolution is very slow. So you have an external parameter, and when something is changing very slowly, you have some invariants there, some things that are constant, and one of those is the volume enclosed by an energy shell, which is this one here. So it's sometimes in microcanonical, the log of this is the entropy, which is actually there is a lot of controversy. What is if this is the log of this is the entropy or the log of the surface? And okay, but this is an adiabatic invariant, which is nice because it's something that doesn't change. And then if phi is 1-to-1, which is 1-to-1 because it's an increasing function, no? Because it's the volume enclosed by the energy. So if the energy, well, in quantum mechanics, it's not always 1-to-1. No, this is always 1-to-1. So if you increase the energy, phi increases. And if it is 1-to-1, and I am in a cycle, and the only possibility is to go back to the same energy. The initial energy and the final energy must be the same because it cannot change. So, and if I have a cycle, of course, all this is when I have a parameter in the Hamiltonian changing. So this can change. If I change my Hamiltonian, I can change. But if I go back to the original state, work should be 0. The energy is. So these two properties, which are like very elementary from the, it tells you that in a quasi-static cycle, work should be 0. And if the cycle is not quasi-static, then it's worse, and work is usually bigger than 0. So why our example defeats this thing? Well, because this is not true when you have ergodicity breaking. The volume enclosed is not here. When I start to move my wall, suddenly, if I start with a shell of energy, suddenly this shell encloses a volume V, and suddenly when the particle gets trapped, and this is like a critical point for the dynamics, boom, the volume enclosed shrinks by factor 2, which is very similar to what happens in the symmetry breaking, but here we don't have to pay the price of uncertainty in the macroscopic world. Here we really know where the particle is. Okay, so sorry. So this is why symmetry breaking is completely necessary to achieve this kind of microcanonical Maxwell demon. There is a variant by Suri and Chris Jarzynski. They wrote a nice paper in 2011, and it's even nicer because there you can. This is the phase space, and Rahul's and my example is more involved because you have the phase space split into two. Here they could make just a shift between, a swap between regions in the phase space. There is a movie which is nice. It's a pity that Suri left because this is probably he did his movie. You see, this is velocity, and this is position, and this is a potential. So now there is this critical point where the greens come here and the reds come there, and the overall effect is that green regions swapped red regions. And of course, if you know the energy, you prepare this protocol for these particles, and you can cool down again the particles. So to end with this story, because one question is, for instance, can you do this with a macroscopic system? Because we could do it with single particle. We tried with two particles, and it was not so easy. But the idea is, can you do these swaps in the phase space with macroscopic systems? And it's an open question. I don't know any example that could do it, and I don't know any proof that you cannot do it. So it's an open question. So we explore a little bit this thing, and I will finish with this result, which is a nice universal equation for in any system, in any cycle, now with symmetry breakings and everything. So suppose you have a system, Hamiltonian, everything is Hamiltonian, in your phase space, and you make a cycle, and then instead of the energy, which is what we at the end is what you want to see. What's the initial energy? What's the final energy? And then you can check if you have extracted work or you have put work. It's much easier. We realize that it's much easier to work with the enclosed volume. So remember, this is the enclosed volume, and we found this nice equation that if U is the final enclosed volume, so this is the map. This U is the map that maps the initial enclosed volume to the final. It's these curves here. Here you have the initial enclosed volume, and here is the final. And we found that whenever you have this ergodicity breaking, you have some probabilities to go left, right, or to go up, down, or wherever. And if these are the probabilities that you have, this function has different branches, and each branch has to obey this equation. And we could plot this equation for Suri's and Jarzynski machine. This is a one-to-one. Suri's machine is a one-to-one. So there is no splitting. There is ergodicity. There are some critical points, but the trajectories, the phase space doesn't split into two. So the probabilities are 1. So this slope is 1, and as you see here, the slope is 1. But the nice thing is that you can, this region, is mapped into this region, and this region is mapped into this region. So it's this shuffle between up and down. And this is our example, the Rahul Marathe and my example, the one that I did with Rahul. And you see here you have some branches but the slope is always obeying this equation. And here is the normal Szilard model, and you can see this in this paper here. So, okay, to finish, remember that we have this explanation of the Maxwell demon, which was a little bit disappointing, and then I said, well, there are two strategies, just to be happy with this and generalize to any kind of evolution and any kind of continuous time and so on, or look back to the concept of information, which has more to do with ergodicity breaking and symmetry breaking, and it has been my slides. Finally, the last point of the course was intended to be an introduction to these information flows, and unfortunately, it was too ambitious, the course, so I just have a slide, which is I refer you to this paper, where they studied, they generalize this to, as I said, to general cases where you have two systems, X and Y, and they are connected somehow, and they compute all the flows of mutual information, the flows of entropy, and this kind of conversion between correlations, mutual information, you see, you do some work to create correlations, and in the feedback, you extract this work, these correlations as work, and so on. They do this in a very general framework with master equations. So, but the main idea is to generalize this to continuous time and systems with many degrees of freedom and so on. So this is the end, and just well, I hope I convinced you that there are a lot of things done and to do in the topic, and maybe the biggest question and the most deepest question in this is what is information? That we know that even we were discussing yesterday, you know that even there are all these people, Seth Joyd and more people trying to build physics out of information, but sometimes one has to go back to the starting point and say, what is information from a physical point of view? And as you have seen in this last lecture, my point of view is that, my point of view is that information has to do with these metastable states or symmetry breaking or ergodicity breaking. Essentially, ergodicity breaking, as we said before, is an effective ergodicity breaking is when you have a huge separation of time scales, and information is in the low degrees of freedom, whereas the physical world is in the fast. But on the other hand, there is this approach by Horowitz and Esposito that it's as creation and annihilation of correlations. More than creation and annihilation is transforming correlations into work and the other way around. So I don't think they are exclusive. As I said, they are contradictory, but they are complementary ways of looking at information. And thank you for attending the course.